Hello class, I hope you're having a wonderful day. In this video, I would like to complete a practice problem from Chapter 1. Remember that Chapter 1 is titled A Physics Toolkit, so it's really a review for algebra, graphing, and dimensional analysis. Okay, so in this problem that I'm going to do today, what we are starting out with is a T-chart. So you see a table of data, and all that is just a T-chart. So remember from algebra, when you started to graph, we had a T-chart with X and Y values, and we have ordered pairs listed. So we had X value 1, Y value 1, and you would graph that ordered pair. Then you had X2, Y2, and you would graph that ordered pair, and so on. Well, you have the same thing going on in a T-chart over here. In the left-hand column, we have time, and I have units of hours, and these are going to be all of the X values. So I'm just going to go ahead and write X right here, okay? And in the right-hand column, we have total rainfall, and these values are the Y values. So we have ordered pairs that we can graph. Now, if you look closely in our T-chart here, we have all positive values for X and all positive values for Y. So that means we're going to graph in quadrant 1 only, okay? So there we have our ordered pairs. I've started to draw the graph here. Here I have my X-axis, here I have my Y-axis. So let's start with number 1 here. It says plot the ordered pairs on the graph, label each axis, and title the graph. So let's label each axis. Right here, I'm going to have time, and we are required to put units on our x-axis. So right here, we have units of hours. Remember to write your hours and put them in parentheses. On our y-axis, so total rainfall, and once again, we're required to write our units down. So I've got total rainfall in units of centimeters, okay? On our x-axis, we're going to start at 0, and on our y-axis, we're going to start at 0. So right here, that's going to be 0, 0, or 0 hours, 0 centimeters of total rainfall. So we're going to go through 48 hours. So I'm going to use a scale of 6. And yes, we go through 48. And then total rainfall. So our maximum value for total rainfall is 5.2 centimeters. So I'm just going to put my upper limit as 6 centimeters on my graph. Okay, and then about halfway, that's going to be 3. About right there. Got 1, 2, 3, 4, and 5. Okay, so we have our axes labeled. We have our scale for both the x and the y axis. It says graph the ordered pairs, label each axis, and title the graph. So on your assignment sheet for this practice problem, it talks about total rainfall in the forest. So let's just simply call this total rainfall in forest. Okay, now let's plot our ordered pairs. So we're going to read from the top to the bottom here. So our first ordered pair is 0, 0. Then I've got 6 and then 0.7, so I'm at 6 hours. So we're going to locate that on the x-axis. 0.7 centimeters of total rainfall. I've got something like that. Then 12 hours, 1 centimeter of total rainfall. 18 hours, 1.8 centimeters of total rainfall. 24 hours, 2.8 centimeters of total rainfall. Then I've got 30 and then 3.1. 36 and 4 42 and 4.6. And then my final ordered pair is 48 hours, 5.2 centimeters of total rainfall. All right? And so there we have all of our ordered pairs plotted. So number one, we're finished with it, taken care of. Number two, create a line of best fit. Okay? So looking at our data, we need to decide what kind of relationship best describes total rainfall versus time. Okay, so what we have is a linear relationship for a line of best fit. So if I drew that, you got something that looks like this. Okay, so we have a linear relationship for the line of best fit. Okay, so we've got a dashed line in here. So this is going to be the average values where they're going to fall on that line of best fit. Okay, number three, calculate the slope of the line. Well, remember, the slope is identified by the rise over the run. Okay, and we know that the rise is the change in y, and the run is the change in x. So slope, which is identified by lowercase m in slope-intercept form, we have delta y divided by delta x. Now remember, this capital Greek letter delta represents change in. So what we're saying is the change in our y value divided by the change in our x value. So if I expand the numerator and the denominator, this is going to give me y2 minus y1 divided by x2 minus x1. Okay? All right, so calculate the slope of the line. So here we go. So y2 minus y1. Well, actually, before we put any values down, I just want to remind you that we're going to read our graph from the left, so starting from the left and then going to the right, okay? So I'm going to identify my last ordered pair. We're going to have, well, this is x1, y1, okay? We want to use the two most extreme points, but I want to identify my second ordered pair. We don't want to get ordered pairs really close because that's probably not going to be the best description of the average slope here. We want to do two really extreme points to describe the slope of that line. I'm looking at my last ordered pair here, and I notice that my line of best fit that I have approximated, drawing on the whiteboard, is actually slightly above my ordered pair. Well, the x value is 48 hours, but my y value for my ordered pair is 5.2. But what I want to do is identify the x value here. And that looks to be about 5.4. So let's do 5.4 centimeters. Okay? All right. And that's going to be right there. So my y2 value is 5.4 centimeters minus y1. Well, we're going to go back to ordered pair 1. y1 is going to be 0 centimeters. I'm going to divide this by x2 minus x1. Well, our second ordered pair, remember, we're reading the graph from the left to the right. x2 is going to be 48 hours minus x1, 0 hours. So let's grab our calculator. All right, I've got 5.4 divided by 48. This is going to give me 0.1125. So the slope of the line, identified by lowercase m, this equals 0.1125. And I have units of centimeters per hour. And those units don't cancel out, okay? So we have to keep them. So in my numerator, I have units of centimeters in my denominator, units of hours, okay? So the slope of the line, 0.1125 centimeters per hour. Number 4, convert your answer to centimeters per day. So, well, let me leave that up there. Okay, so what we're going to do now is use dimensional analysis. And remember, dimensional analysis is the process of treating your units as algebraic quantities in order to cancel units. Now, we need a conversion factor here first. So, we have centimeters per day. That's what we want the units in. Right now, we're in units of centimeters per hour. You know that there are 24 hours in one day. So, we are going to multiply by a ratio that's going to cancel out units of hours and leave us with units of days. So, let's go ahead and write our value here. 0.1125 centimeters per hour. Okay, we know the conversion. There's 24 hours in one day. So what I'm going to do is multiply by a ratio that's going to cancel units of hours. So in my numerator, 24 hours divided by 1 day. Here I have units of hours in my denominator. Here I have units of hours in my numerator. Boom, those are going to cancel out, okay? Now we're going to multiply. I've got 0.1125 times 24. Okay, this is going to give me 2.7. 2.7. Now I'm going to be left with units of centimeters per day. Okay? And that will be my answer for units of centimeters per day. All right, let's move on to number 5. Number 5 says identify the y-intercept with correct units. So I'm looking at my line of best fit here, okay? And our first ordered pair is 0, 0. And so my y-intercept, we must include units, is going to be 0 centimeters. So y-intercept is equal to 0 centimeters, all right? Number 6, an equation to describe the relationship shown. Okay, we've already identified that we have a linear relationship for the line of best fit. Well, let's go ahead and write an equation for this. Now, it's going to fit the form of slope-intercept. So I've got y is equal to mx plus b. But now that we're in physics, we need to be more descriptive. So we need to use this base equation and apply it to our situations. So the first question we need to ask ourselves, what do all of these variables represent? Okay, then we're going to apply it to our situation. Well, you know y is the dependent variable. M represents the slope of the line, which you guys have already calculated. So the slope of the line. X is our independent variable. And remember, this independent variable is the variable that is changed or manipulated in your experiment or your equation. B is the y-intercept. And you guys have already identified that. That's 0 centimeters, okay? So instead of writing y, our dependent variable is total rainfall. So that's what we're going to write. I've got total rainfall is equal to the slope of the line, okay? Let's go back up here to number 3, the slope of the line. We have units of centimeters per hour. Now, right here in number 4, we perform dimensional analysis to get it into centimeters per day. But I want to keep it in this form of centimeters per hour because our graph has centimeters per hour, okay? So 0.1125 centimeters per hour times x, this is our independent variable. Well, our independent variable is time. So lowercase t to represent time plus our y-intercept. Well, you already know that the y-intercept is 0 centimeters. So do we really need to write plus 0 centimeters? Absolutely not. So the equation to describe the relationship shown is right here. So I'm going to rewrite that over here. So total rainfall is equal to 0.1125, and we have units of centimeters per hour times our time in units of hours, okay? All right, on number 7, could the graph recording total rainfall ever have a negative slope, and why? So, let me erase this business here. Let's think about this. Could the graph recording total rainfall ever have a negative slope? And then it wants us to describe why. So I'm taking a look at total rainfall versus time for the total rainfall in the forest. So what we're doing is recording how much rainfall we have at a particular time. It's like we're hitting a stopwatch. We have units of hours, and we have something to measure the total rainfall, okay? So it's raining more and more, so that means we have a positive slope here, okay? As time increases, as time goes on, we're receiving more rainfall, okay? So we have a positive slope on our graph. Let's just say that the rainfall stopped. It totally stopped raining, okay? So let's say we're right up here. The rainfall stops raining after 48 hours. What is our graph going to look like? Well, if we have no more rainfall, our total rainfall would still be 5.2 centimeters, okay? And as time goes on, we have no more rainfall, but we still have 5.2 centimeters. So, can it have a negative slope? The answer is no. So I'm just going to go ahead and write no. It cannot. Because if rain stops falling, we're going to have a horizontal line. And you know that the slope of a horizontal line is 0. So my slope would equal 0 centimeters per hour if there was no more rainfall. All right, so we can have a slope of 0, but we can never have a negative slope when we're describing total rainfall. Okay, well, I hope me working through this problem helped you out today. As always, if you have any questions, you can always email me, you can give me a call, or you can contact me over the Canvas. Okay, well, I hope you have a wonderful day.